So let's go ahead and do this. So this is going to involve some integration, calculus and all that.
Okay.
So you will have to keep me honest with all my derivations.
Absolutely.
Okay. So what did we do, by the way, when we derived the step response? We solved a differential equation.
Yes.
Right? RC. So V of t, I'll just call it V in, and we are going to observe the V out, Vc of t. Okay.
Yeah.
So we applied KVL around this loop and just said V in, okay, or I said small v in, right? V in of t equals, let's call the current I into R, okay, I of t actually, plus Vc of t.
Yes.
Right? Now the current I is equal to C into dVc by dt. Therefore, we got the following, right? We said RC dVc by dt
Yes.
plus
Vc
Vc equals
V in of
V in of t. Okay. Now I'm going to divide by RC, okay, dVc by dt plus 1 by RC
Yes.
Vc of t equals 1 by RC, and now I'll substitute this V in of t. We are looking at a sine omega naught t.
Yes.
Okay. So
Yes.
I will simply now, I will call this as some constant for now. Okay. I'll call it some k times sine omega naught t.
Yeah.
Right. So when we did the step response, we encountered a very similar differential equation. Okay. And what we saw there was, if you had dy by dt plus p into y equals q, where both p and q are functions of time, the solution to this equation was e power integral p dt equals integral q of t e power integral p dt times dt plus a constant.
Yes.
Right? So
Yes.
this is what we did. We have exactly the same situation here. P of t happens to be 1 over RC. Q of t in this case happens to be some k times
Sine omega naught
sine
t.
of omega naught t. Okay? So
Yes.
therefore, let's go ahead and try to solve this equation, right?
Yes.
So we have y into e power integral dt by RC, okay, equals integral k sine omega naught t into e power. So this e power dt by RC is just e power t by RC.
Correct.
So I will replace that by t by RC dt plus a constant.
That's right.
Okay. So effectively, if we know how to solve this integral,
Yes.
we are done. Okay.
Correct.
So therefore, I will start with that separately. We effectively have an integral of the form e power a t sine of bt dt. Okay, it's an indefinite integral.
Right.
So how do you suggest we solve this?
So let me take a guess. Maybe you can go back to the differential equation. I'm going to observe something. Actually, even the previous one with the sinusoid.
Yeah.
So you wrote it in this form, right?
Yeah.
So RC dVc by dt plus Vc of t is some 1 over is some a sine omega naught t.
Yeah.
Right. So I'm going to take a guess. So what this is telling me, I'm differentiating this capacitor voltage.
Yes.
I'm scaling it.
Yeah.
And then I'm adding it to the capacitor voltage.
Yeah.
I'm getting a sinusoid.
Yes.
Right?
Correct.
So I'm going to take a guess. I don't know if it's true or not.
Yeah.
But I'm guessing I'm going to bring some trigonometry. I remember that if you differentiate a sine, you get a cosine.
Yes.
You differentiate a cosine, you get a sine.
Yes.
And also cosine and sine are delayed versions of each other.
Yeah.
Right.
Correct.
So if I imagine that the result Vc of t is going to be a sinusoid.
Yeah.
If I differentiate it, it's going to be a scaled sinusoid again.
It will be a scaled sinusoid.
Right.
Yes,
So
absolutely.
I can imagine that the result may have a sinusoidal, it may be some kind of sinusoidal function.
Okay.
This is my guess.
Okay.
Okay.
guess your VC of t, you're saying is some sine of, we don't know, some omega 1 t
Yes.
plus some
I don't know
phase
phi, correct, and some amplitude as well.
Amplitude A1.
Correct.
Right? This is your guess. I
This is
think
my
that
guess.
makes a lot of sense, based on your very intuitive arguments here, right? So we'll come back and see if the
Yes.
rigorous derivation also gives us this now. But now, have you done some integral like this in your 12th standard?
Yes, and I think there is a way to separate it into two parts
Yeah.
and then solve it.
So essentially, we go back to first of all the differentiation chain rule,
Yes.
right? dt of uv
Yes.
is u dv by dt plus v du by dt.
Yes.
Right? Now if I just reorder this, it implies u dv by dt times dt,
Yes.
right? Integral I can write as uv minus v du by dt into dt.
Yes. Integral. Correct.
We can write it like this, right?
That's
So
right,
this
yes.
is by parts, doing integration by parts.
Parts. Yes.
And this is what we are going to do. So what we will do is, we will just say, for example, that this is my u, okay, and this is my dv by dt,
Yes.
okay. So what I am going to do, I will say therefore integral e power a t sine of bt into dt is u into v, okay.
Yes.
So I am going to say e power a t, if I need v, right,
need
this
v.
is dv by dt,
Correct.
so I get 1 by a
1 by a, right,
into u,
which is sin bt.
sine of bt, okay,
Okay.
minus integral, again the v is going to come out like this,
Yes.
v of a t by a into du by dt now. So I'll get b times, what you
Cos.
mentioned,
Correct.
cos,
I see it now. That's
yeah,
right.
right? You
Yes.
see this,
Yes.
okay? So still this doesn't give us the answer though, okay? So I'll have to write this a little carefully, e power a t sine of bt minus b by a integral e power a t cos of bt
Yes.
dt, okay. So I will call this as my integral I, okay. Now this you see is again of the similar form as
Yes.
I.
Yes.
So therefore I'll do this rule again, right? I'll do this rule again and I'll retain this term e power a t sine of bt minus b by a,
Yes.
okay, e power a t by a
Yes.
cos of bt
Yes.
minus integral e power a t by a. I have to differentiate, cos bt now. I'll get minus sign, right?
That's right.
So minus b times bt dt.
Perfect.
Okay.
Yeah.
So we have an interesting thing because maybe I'll this e power a t sine bt dt is back to the original integral that we wanted to solve.
Correct.
Okay, so I will just
Maybe you can write it in terms of I.
exactly. I am going to write it in terms of I. So therefore, I will say I is equal to, okay, there is 1 by a e power a t sine bt.
Yes.
Okay, 1 by a e power a t sine bt, okay,
Minus b by a, so b by a squared.
yes, minus b by a squared e power a t cos bt,
Yes.
and then I have
Plus, oh, So
No.
this is also again
This negative sign is sort of going to cancel.
Going to cancel. So
I'll retain the minus sign.
So you'll have minus b squared by a squared.
Minus b squared by a squared, exactly.
Yes.
Right? Minus b squared by a squared into I.
Yes.
Because that e power at sin bt dt is back.
Yes.
Right? So now I will just reorder this, bring this term here. Implies I into 1 plus b squared by a squared, right, equals e power a t, I'll keep that a outside, okay, sine of bt minus b by a cos of bt, okay, which implies I effectively is going to be the a squared will go on top, it will get cancelled, a by a squared plus b squared e power a t, okay, into sine of bt. I will take this a here, okay, and pull it out of the bracket. So a sine bt minus b cos of bt,
perfect,
right, divided by a, 1 by a. So that goes, okay, and now I have a very interesting expression.
Yes.
Okay, a sin bt minus b cos of bt. Okay. So here we have solved that integral, and your guess was this was of the form some a1 sin omega naught t plus phi or something like that,
correct,
right?
Correct.
But it's not clear that we already have that form, right?
Yes.
So how do we do this? Now just imagine this, okay? Suppose you had a, right? So I'm going to say this is a right angle triangle. Then this is going to be root of a squared plus b squared.
Yes.
Suppose this angle is phi.
Yes.
Then sin phi will be b by root of a squared plus b squared. Cos phi will be a by, right?
Yes.
So what I'll do is this a squared plus b squared, I'm going to split it as e power a t by root of a squared plus b squared, okay, into a by root of a squared plus b squared sine of bt minus b by root of a squared plus b squared cos of bt. Okay.
Okay.
So this you can clearly see is going to be cos phi.
Yes.
Right. This is cos of phi.
Yes.
And therefore this has to be automatically
Sin phi.
sine of phi.
Yes.
Right. And therefore I can write this integral as e power a t divided by root of a squared plus b squared into, just take a look at that, it's
So
sin bt cos phi, minus cos bt sin phi. So this is a very well known trigonometric identity.
That's right.
It has to be sine of bt minus phi.
Minus phi.
Right. So into sine of bt minus phi.
Perfect.
Okay. So note how these constants came out beautifully. Okay, we got a, we got b, and we got root of a squared plus b squared here, right? That's why it was, so we were able to do it so nicely here.
Right. That's
right. So effectively our integral I is of this form, and what was a? It was 1 by RC.
1 by RC.
Right. So let's just write down those values. A was
I think it was it 1 by RC or a by RC? Because the input amplitude was capital A, did we choose that? Yes, it was capital A by RC.
No, this is K.
Oh, this is
constant.
That is the constant.
Right? This is the A.
That is A,
right?
1 by RC.
We basically got it to this form, e power a t, right? E power t by RC sine omega naught t. The K is outside.
K is outside, everything.
Okay, yeah. So therefore, A is 1 by RC, B is omega naught.
Omega naught.
Right?
That's right.
So effectively, our integral was very interesting. We got e power t by RC by root of omega naught squared plus 1 by r squared c squared, okay, sine of omega naught t minus
phi. And phi is clearly needs to be tan inverse.
phi. What did we get phi?
So we have
Phi
B and
is, so tan phi
yes is
equals
B by A.
B by A,
Yes.
essentially, right? So tan equal to B by A, that is omega naught by 1 by RC.
So times
into RC.
Perfect.
Okay?
Okay, great.
And therefore, your guess was 100% right.
Okay.
Vc of t seems to have this form, okay?
Right.
But let's go and just complete the equation, right? We basically said that the integral was this value, okay? So
Yes.
y into e power t by RC, okay? Therefore, I can divide by this e power t by RC and make it constant times e power minus t by RC.
Correct.
Okay. So, what do I have here? Vc of t, okay, is going to be the t by RC, therefore will go to the constant,
Correct.
okay. 1 by root of omega naught squared plus 1 by r squared c squared into k times sine omega naught t minus phi plus constant times e power minus
T by RC.
t by RC.
Okay.
So, now this term is essentially a transient response, right?
So if I were to imagine before I apply the sinusoid, maybe the capacitor has some initial charge
Exactly.
that will have to discharge.
Exactly, right?
Right?
But eventually it's this sinusoid that's going to take over, right? So
Correct.
we are not, so in fact, when we looked at the output voltage, we don't even remember at what point, where we started. We are just looking at the sinusoid going, right? So therefore this we will just neglect for now. We are not going to be worried about it. The steady state response for Vc of t is essentially going to follow this form, okay? And what was k? We said k was a by
RC.
RC,
Yes.
okay? Therefore, I will say Vc of t, I am going to do a small thing, I am going to omega naught squared plus 1 by r squared c squared, I will take the RC on top, right, and bring it out of the root on top, okay,
Yes.
there, right. So, it will be RC by square root of 1 plus omega naught squared r squared c squared
Yes.
into a by RC sine of omega naught t minus phi,
Yes.
and tan phi is omega naught RC. Therefore, this implies Vc of t is a by root of 1 plus omega naught squared r squared c squared,
Okay.
okay, into sine of omega naught t minus phi.
Okay.
Okay. So, this is the steady state response for this sinusoidal input. And now let us go back and see the two observations that we made. We said that the amplitude falls off as the frequency increases, right? So, we see here there is a thing. So, the amplitude of the sine wave A out, right, is A by root of 1 plus omega naught squared r squared into c squared.
Yes. So in fact, I am guessing that if I make omega naught quite large, in fact, if I make omega naught RC whole squared much larger than 1,
yeah,
then the amplitude should approach actually A by omega naught RC.
Exactly.
And it will go down, looks like it will go down linearly, almost,
linear.
I mean, not linearly, inverse. It goes as the inverse of
Correct,
omega
exactly.
naught.
Yeah, you are right. So, if omega naught RC is much greater than 1, then implies A out
Yes.
will tend to A by
Omega naught RC.
omega naught
Right.
RC,
So if I double omega naught, the amplitude will fall by half,
fall by half,
right? For large omega
right,
naught.
for large. But initially that is not true.
Initially, that's
Right?
not true.
And but what happens when omega naught RC is very close to 0? Because
Yes.
when we took a 100 hertz sine wave
Right.
with respect to the RC that was 100 microseconds, this omega naught RC was a very small number.
Yes.
It'll,
It's
so
almost the same amplitude A.
exactly. If omega naught RC tends to 0, implies A out equal to A.
That's right. That's
and
right.
this is exactly what we saw.
That's right.
The output follows the input not only in amplitude but also in phase.
In
now,
phase.
let's not forget
Right?
that.
Correct.
So what happens if omega naught RC is a very small number, right? Then tan phi is a very small number,
Very small number.
and which means it's very close to 0.
Correct. So
right?
the phase shift will be very
the
small.
phase shift has to be very small, right?
Yes.
Now, but we had another interesting observation. We said that the phase very quickly goes away to pi by 2
Yes.
and then sort of saturates there.
Yes.
So why is that happening?
In fact, I can see that when omega naught RC is equal to 1,
Yeah,
right? Tan phi is 1,
exactly.
and which means phi is 45 degrees. Pi by
Exactly,
4.
right? That's another interesting observation. So omega naught RC equal to 1, okay, implies tan of phi should be equal to
1,
1, yeah,
which
implies
means phi is pi
phi
by 4.
is pi by 4.
Yes.
So why don't we go and see this? Check
Yes.
this out now, right?
Yes.
So omega naught,
And in fact, we can also check the amplitude at this point.
yes, we can also check the
Right.
amplitude, yes. So this is what we are saying 2 pi f naught RC
Yes.
equal to 1. In fact, you alluded to this earlier, you called it radians per second, right?
Radians per second,
Okay,
correct.
exactly. So implies f naught is 1 by 2 pi RC.
Yes.
So what is this? So this is the 1 by RC.
So I think R was 1 kilohertz. And
Yeah. So this was
yes,
100 microseconds.
100 microseconds. Correct.
Okay.
That's right.
So what is this approximately?
This is probably like, let me see. So 100 microseconds is 10 kilohertz, maybe a few kilohertz,
Yeah.
right?
So maybe 10 by 6
Yes.
kilohertz.
Yeah, 1.6, something like that.
Yeah.
Yeah.
Right? 1.6 kilohertz or something like that.
Yes.
So at around 1 kilohertz,
Yes.
we should see the phase shift go close to 45 degrees.
That's right.
Right?
That's
That's
right.
what we want. So
That's
let's
right.
go back there now. I'm going to change this to 1 kilohertz. Okay. And so what is the meaning of 45 degrees? When the orange, the output capacitor is 0,
Yes.
the input should be at what value?
Maybe, let me see. We definitely know it should be far away, somewhere in between, far away from the peak and the zero crossings.
Yes.
Right? One of them is 0, the other is pi by 2.
Yeah.
So somewhere in between. I would
Exactly,
say.
right? So effectively, so what we are expecting is, let's go back here, when the phi is exactly 45 degrees, okay? And what is the amplitude, by the way? That's the other
interesting thing, right?
The other interesting thing is the amplitude. So the amplitude is A by
Root of
square root of
1 plus omega naught squared.
R squared C squared,
Yes.
right? And that we are saying is 1
It's A by root 2.
A by root 2.
So 1 over 1.4.
Yeah.
That's about 0.7 actually.
It should be about 0.7 volts.
In fact, it is.
This, yeah, because remember we have an error. It's about
Yes.
approximately 1.4 kilohertz.
Yes.
But we are giving, so can we give a number here? I think so.
Yes.
Excellent. So now we'll go and see what happens. You see now the output has fallen to about 0.7.
0.7. Yes.
Right?
Yes.
The output has fallen to 0.7.
Yes.
And is this 45 degrees?
I can zoom in and check.
Sorry, I should make it lower. Yeah.
Well, the way to find out
Yeah.
is to maybe look at the delay
Yeah.
in this and then try to
Correct.
confirm, right? So
So
delay
the
is
0
about,
is
about a 0.1 milliseconds.
0.1 milliseconds.
Approximately. If
Yeah.
they're just eyeballing it.
Yeah, 0.1 milliseconds. And
Yes.
the time period is what? 714 microseconds.
714 microseconds.
Right? And
Yes.
what is that? Is 0.7 milliseconds, is it?
Yes.
And what is this? 0.1.
Yeah. close to 0.1.
Okay, so the delay equal to 0.1 millisecond and the
Yes.
time period is 0.7 milliseconds,
Correct.
right? That's
Correct.
what we got here, right?
Yes.
Exactly. So therefore, the delay by t is how much?
This is about 0.14, is that right? 1 by 7, right?
Yeah, 1 by 7.
I think that's 1 by 7.
Yeah,
And I think that's about 0.14 if I'm not mistaken.
0.14. And what we want here is the delay.
So this delay by t will it come out in radians?
The delay by t. So essentially, okay, that's a good point. So we want omega naught t to sort of be equal to this phi, is it?
Yes, correct.
Right? So
Correct.
we have omega naught. So what is omega naught? It is the omega naught is
What is the best way to represent it? Maybe we should
Yeah.
represent it as, so we have a sine of omega naught t minus phi,
yeah,
right?
Yeah.
And we want to bring the phi as a delay.
yes.
So we want to write it as sine of omega naught into t minus tau.
T
Something
minus
like that?
tau, exactly.
Something like
So
that?
what we want, exactly, that's a good point. So we want Vc of t to be written as some amplitude a1 sine of omega naught into t minus tau.
Yes, something
Exactly,
like this.
right? So what we want is omega naught tau to be equal to the phase,
That's right.
right?
That's
so
right.
what we have is, we know omega naught,
Yes,
which is 2 pi into f naught.
f naught.
This is 2 pi into some what? 1.4 kilohertz. So what is it?
Points, no, yes, that's right.
1.4 kilohertz.
1.4 kilohertz.
Right?
Correct.
And we know
Tau is 0.1.
0.1 milliseconds.
Yes.
Right? Implies 2 pi into 1.4 kilohertz into
Into 0.1.
0.1 millisecond
Yes.
equal to the
Phi. In radians.
in radians.
Yes.
Right? Therefore, what do we get? 2 pi into 0.14 equal to phi.
Yes.
Right?
So 6.28.
Yeah.
Maybe this is a good time because we are having a lot of decimals.
Yes.
We need to pull up a calculator.
Yes. Can you
right?
can you please pull
Yes.
up a calculator
Let
and
me pull up
tell
a
me this
calculator
number?
and I'll tell you the number.
Yes.
Right. So let me just give me a second. I will pull up the calculator and I'll tell you. So 6.28 into.
Yeah. Actually, what we wanted was pi by 4, right?
Yes, correct.
That is 0.25.
That's right.
0.25 pi, and
Correct.
this is 0.28 pi.
It is 0.28 pi.
Right?
Very
So
close.
we got it.
That's right. You're right.
Exactly.
You can look at it that way as well. That's
right?
much easier, in
2
fact.
pi
Right?
into 0.14
That's much easier.
is
That's
equal
right.
to 0.28 pi.
Perfect.
So we see that when we give that frequency, the exact, you know, that 1 by RC,
1 by RC.
right, exact value when we give it, the amplitude falls off to 0.7 times.
That's right.
And the phase also shifts by pi by 4.
Perfect.
Right. The final point that I would like to just finish with is, you know, we spoke about the fact that the phase moves very quickly to pi by 2
Yes.
and then sort of saturates. It moves towards pi by 2 and then saturates, right?
Yes.
So that also, so if you look at phi, it is nothing but tan inverse of,
Yes. Tan
Right.
inverse of omega naught RC.
so all we have to do is, how does tan inverse of x?
Oh, yes. So we can clearly see this because omega naught is positive, R is positive, C is positive.
Exactly.
So it can only go from 0 to infinity.
Yes.
Right?
Right. So here, if you look at this, something like this is how the tan inverse x looks.
Yes,
right?
that's right.
This is at
Pi by 2.
pi by 2
Perfect.
because the omega naught RC. So we are looking at out here as a function of omega naught, and we are looking at tan inverse omega naught RC.
Yes.
Right? So it will go very quickly. It will go, if you look at this trajectory, it goes and then it sort of saturates. It will
That's
keep
right.
getting closer and closer to pi
pi
by
by
2
2.
slowly, asymptotically. The same RC kind of behavior that we saw. Asymptotically it gets to pi by 2,
Yes.
but it will never get there
It
unless
will never
you go
hit
to
there. Correct.
infinity.
In fact, this is showing that if you just use a single R and single C,
Yeah.
it seems like you can never generate a phase shift. If you want to look at the phase shift,
Yeah.
you can never get phase shift larger than pi by 2.
Exactly.
If you have a single R and single C.
Exactly.
Right?
Exactly.
The amplitude keeps getting smaller and smaller, but the phase shift just saturates at pi by 2.
Exactly.
Very interesting.
Right?
Very interesting.
So that's a very interesting thing. So, just to tie all this back, where we started off with, right? We basically said what happens to the frequency. So we saw that your amplitude, right? Output amplitude here, this is A out, by the way,
Yes.
essentially looks, like this, A by 1 by root of omega naught squared R squared. So what we see is lower frequencies with respect to RC are unaffected,
That's
the
right.
amplitude, higher frequencies are suppressed.
Right?
And therefore, this is commonly known as a low pass
Okay.
filter. This basically filters out frequencies.
Makes sense, because we know what filtering something means.
Exactly.
It keeps some solids and lets the liquids go past. That's a filter.
Exactly, right? So it's exactly intuitively the same thing that it does here. It keeps the low frequencies, allows them to pass. High frequencies are filtered out. And what does this mean coming back to our SPB concert? It means that if you wanted to amplify a guitar, but
Yes.
not, let's say, the bass guitar.
The bass guitar,
right?
yes.
Then the frequencies of these two instruments are very different. You could build a filter like this, right? And in
okay.
fact, in that mixer, you have not just a master volume control, which was that resistive network we saw,
That's right.
but you also have this equalizer, which will allow you to control frequency dependent amplitude control.
I see. Okay.
Right?
Okay.
And effectively, a mix of all this is what will ensure that we listen to the concert.
The best possible audio quality.
Exactly. So in fact, in the
Experience.
first lecture, I remember you spoke about there were multiple feedback monitors
That's
on
right.
stage.
That's right.
So a bass guitarist needs to hear his own or her own guitar properly, right? So for
Yes.
that, the bass frequencies will be amplified.
with respect to the other
Frequencies. And of course, he'll be listening to some percussion or whatever it is, right? But all the other frequencies have to be lowered.
Suppressed.
But the audience will not listen to it like that, right? And neither will the musician's feedback monitor. The vocalist's feedback monitor will have a very different mix in terms of even this frequency dependent control,
Perfect.
right? So we'll stop here and we'll continue in the next lecture.
Great.